It's great to be here. Uh, so we've heard some fantastic talks about Antarctica, the oceans, asteroids, the sun. I get the privilege to talk about the universe. And I understand that if you don't do this every day, the universe and talks around the universe can seem a bit abstract. And so I'm going to work on trying to give, in the middle of there, a sort of a cosmology 101 to what you need in order to appreciate what comes out of Euclid very soon. I also chair the UK Space Agency Science Programme Advisory Committee, and I'll flag that first because we're at a very interesting stage sort of in science programs in 2023. We are in the middle of cosmic vision. We've seen this year the launch of JUICE and Euclid, which are major milestones of the cosmic vision program. We have also sort of understood what the end of the cosmic vision program will look like. So we've kind of bookended the end of cosmic vision, and we're being asked for our advice and the UK position on what the future of the ESA program should look like. So next year, the committee I chair will be hosting a series of 3 workshops where we try to bring in that community input of how our science goals, our technology goals can all feed together, and we can go work with our European partners. Now, my own personal view is that I think the ESA program is fantastic. Great science is coming out. We've understood from Horizon and through Cosmic Vision, I think we've refined how we do these medium-class missions. Over the last 12 months, there's been an issue about the L-class missions, and if anybody has followed the history of LISA and Athena, you'll know that there's been issues around the cost cap. They were well over their cost cap of 1.3 billion a year ago, and now they're sort of on track. The order has flipped, but I'd say the program, I think we're on top of how that program works at the big level. The small level has been a bit experimental. There's been a small mission by Switzerland called Cheops. There's been a small mission done in collaboration with China, which has only gotten more difficult as the decade has progressed. Very challenging. We've got an F-class mission, Comet Interceptor, and then there's a question about whether the European Space Agency has the right mechanisms to do something that's F-fast. And I think that's something we need to look into. And the second F-class mission has recently been picked. I couldn't find a picture. That's Arrakis. And so I would say my feeling is at the bottom, the small class is still a little bit experimental. And so when I look at this program, I notice 2 things. We're still a bit experimental at the small end, and I think we need to talk a little bit about the big end. And I'll do that in a minute. But my main focus will be on Euclid itself. I'll dig in there. Since Euclid is just launched and it'll start collecting its science data next year, I thought now would be the right time to reflect a little bit on the history and see what we can learn that will help us with the program. It's great to have you here, David Southwood, in the audience, because you had a strong part to play. David sort of helicoptered at the top while Euclid was going on, guiding it through, and I was more a minion on the ground at the coalface, working it through. So you'll get my perspective, and maybe later you'll get David's perspective. But David actually had a big impact on Euclid all the way back in 2001. You gave a very good talk in Pomona in California, and I was a young graduate student there, easily influenced, and it was a fantastic talk. I remember 2 things you said. You had a little vial of red paint, Ferrari red for the red planet. I don't know why that stuck, that did. And then you talked about the economics of Europe, that the European economy is bigger than the US economy. And so anything they can do, paraphrasing, anything they can do, we can do. And it's just a question of will. And of course, being young and naive, I've carried that through. And a lot of themes are going to come back to that idea that anything they can do, we as Europeans should do too. Now, that may have caused you some problems a bit later, as you'll see, but you'll see that that's really a part of the Euclid story. Before I get into that, though, let me just talk a little bit about that future program. The meetings I've been at ESA, we go around the table, the 22 member states, and it feels like we're saying different things at the small end. You know, some big countries say we should only be doing this, other countries say we should be doing this size. But actually, if you listen very carefully, everybody's saying precisely the same thing. ESA should take over where a member state can't do it anymore, right? ESA should support a member state to get things that are out of its reach. The problem is there's very many different member states. So on my last trip to ESA headquarters, on the way back, myself and Ryan King sat on Eurostar and we worked through an Excel spreadsheet, because that's what you do, right? You work through data to kill the time. And the thought experiment is this: if you're a member state, how much money can you put into one mission over 10 years? Okay, if you put all that into one mission, you will lead it, you're in charge, you get to put your flag on it. Very good. If you choose a partner, you can double your reach, right? So you can do a mission now that's twice as big, still stick your flag on it, be very proud, get Norway or Denmark or whoever behind you. If you go all the way down to being a 20% partner, you're still a significant partner, and you can be quite proud of it. But if you're a 20% partner and the other partner is ESA, then it's really interesting. You can still claim to be the biggest member state driving a mission and stick your flag on it. And for me, I think my argument to you is that's probably the maximum reach that you can get before you're no longer the lead country. So it's whatever you can afford times 5 would be my guess. I've put this to various delegates and they seem to agree. And so it's very simple. I talked to a few of them, I pinned it down, I created a regression, I used some GDP data and then a boost thing based on a country's fondness of space, and produced this. All right, and I think this is a really interesting plot. So if you look over here, you have the large countries have a reach of, well, France, according to my simple model, has a reach of about 400 million euros. So suddenly, France not being interested in anything below an M class makes a lot of sense. Here, UK and Spain have a reach of about 250 million, and UK and Spain are currently dominating the F-class mission umbrella. But you'll notice most member states, their reach hits about 50 million. Now, you know, this isn't a great model, could be 50, could be 100, somewhere in that range, which helps, I think, explain some of the feedback I got from colleagues, which is when they go to their communities for some of these member states, and they talk about an F-class mission, the community's not interested because it's so far out of reach that they might as well be minor partners on a much bigger mission. So I think that's a challenge. That's something we have to reflect on and see how can we work through the bottom end. Let's talk about the top end, because as David made me think, anything they can do, we can do. And the biggest missions in the world are not $1 billion missions. NASA's talking about $10 billion, $20 billion missions. As a European scientist, as a community, surely we need to have access to contributions to the biggest experiments being done in the world. And I think that's something we just need to understand. How do we systemize our relationship with experiments at the level of JWST? So I think going forward, I would say there's something at the bottom end to do, and there's something at the top end to also explain. Going forward, though, let's dig into Euclid. This is Cosmology 101. And again, I understand it's an abstract concept, and there's a lot of details when we get into cosmology. But actually, if you take a step back, the universe is very simple, and cosmologists are actually, we're all quite simple. We can't do complicated things like asteroids, but we can do the universe because we actually care about two things. We care about things to do with the distances between objects. We call this technically geometry, the geometry of the universe. It sounds fancy, but it's just really to do with the relationship of distances between things, typically galaxies. So that's one thing we care about. And the other thing we care about is how lumpy the universe is, right? Because when you look around, this isn't a smooth, homogeneous universe. We have lumps, we have galaxies, we have clusters. That lumpiness tells you about what's going on. It tells you we have dark matter. It tells you we've got dark energy. It tells you how much of all the chemicals we have. So that's it. Everything we always talk about affects the distance between things, and it affects how lumpy the universe is. So when you pick something like dark energy, well, dark energy affects the universe because it stretches the universe. And when it stretches the universe, it changes the distance between things. So if we measure the distance between things, we can understand how dark energy would affect the universe. Dark energy also, because it stretches space-time, it makes the universe less lumpy. So if we can see how the lumps grow over cosmic time, we'll understand what the underlying physics was, which is dark energy. So we care about two things, and dark energy affects the two things. The technique I care about the most is a technique known as gravitational lensing. Now, it turns out gravitational lensing, if you imagine holding a magnifying glass, move it back and forward, the image changes, right? Because magnifying glasses and gravitational lenses care about the distance between things, right? And then if your magnifying glass changes strength and the lumpiness changes strength, you'll be able to measure the thing you care about. So the lumpier the universe, the more magnifying glasses we have, and the more lensing we would get. All right? So cosmology is basically this, right? Done a lot more fancy. So if we look at dark energy is a thing that we've kind of has been floating around in the community since the early 80s. As we started to understand how the early universe came together, we started to realize that the universe had to have this weird thing. There was a gap between what we could see and what we call the geometry of the universe. And as time went by, you know, it's a weird thing, dark energy. It just doesn't make any sense. It doesn't fit into normal physics. So you can imagine the community was resistant. But as the evidence mounted over the 90s, more and more people start to talk about this weird thing, maybe. And by the end of the 1990s, by the time we got these latest supernova results, that was it. It was a nail in the coffin. The entire community suddenly switched to, okay, the universe is dominated by dark energy. This is a thing. And very quickly, that became the paradigm. So going into 2000, we entered what was an incredibly exciting and dynamic time in the field. This new thing, dark energy, spun up lots and lots and lots of ideas about what we should do to go for it. The real lead, way ahead of everybody else, was an experiment called SNAP, led by the Nobel Prize winner Sol Perlmutter. And the idea was to do more of that supernova measurement that nailed the dark energy measurement into, as a thing. The US, the Department of Energy, had spent tens of millions of dollars on this experiment. The concept was well defined, and they were ready to go. As part of that, though, Europe was starting to build momentum, wanting to do some work in this area, and also different techniques for measuring the universe were being developed. So I talked about gravitational lensing. Weak gravitational lensing, the technique Euclid focuses on, was only first detected in 2000. So by about 2004, this is a very new technique, really at the cusp of doing anything useful. Some friends of mine, Jason Rhodes, Richard Massey, and Alex Refrigier, who were working on the SNAP mission, started to look at what the constraints would look like for weak lensing from a telescope like SNAP, because clearly dark energy was dominated by the US. And to this day, all but one of the major dark energy missions of the world are done by the US. So the only question at the time was, how do you get involved in this? And then, this is where I came into the game. Alex and I went to France and we started a phase 0 study to look, let's lean into this new technique, gravitational lensing, and what would happen if you design the entire experiment for this. Okay? And maybe we could do it so cheap that France could lead it itself. Turns out that didn't work. And we had to be quite creative. So we leaned very heavily on a new principle of ground-space synergy. So only do in space what needs to be done in space and leave what can be done on the ground to the ground. this was a ridiculous idea, right? Completely ridiculous, because US dominates this. SNAP was so advanced. There was basically 2 of us and maybe 3 or 4 engineers working on the project. It was a ridiculous thing to do. But the head of the lab was supportive, so I was really happy with that. Until the end of the study, I remember we were in a taxi on the way back from our CNES study, and the head of the lab told us, he looked us in the eye, said, "The work that you 2 have done is really great. This will help us secure a big instrument part in SNAP." And I was like, oh no, not even the head of the lab believes in this project. So anyway, it was too expensive to be done alone by France. We needed a partner. We traveled around the world trying to find that partner. And at that moment, the cosmic vision call came up, and that seemed to be the right path. And the key, I think somebody was saying, you know, we've heard a lot about space being a team game. The key was building the consortium and building momentum and bringing people on board. We had a good concept, we grew it, we brought the team on board. We had some very painful processes. We merged with another mission, formed Euclid, and then for a brief period, Euclid got merged with the American mission to form a mission called IDEX. That merger was not going well. They pulled 2 scientists into the team, started to go a bit better. Suddenly we get a call that it got cancelled. I believe David pulled the plug on that, rightly so, and it went back to being Euclid. And by 2001, Euclid got selected and went into production. I won't tell the story of its build. I don't have time. But that's how we got all the way through. And that was really an extremely dynamic decade for anybody who works in my field. And where we stand now is Euclid has just launched. At the same time, remember I talked about ground space synergy. Our partner was what was called the LSST, now the Rubin Observatory. That's, you know, Euclid's a 1.4 billion pound experiment. Rubin is a £1 billion experiment and has been built, starts taking data, and the 2 are going to work remarkably well together. And the evolution of SNAP through a very long path has now become the Roman Observatory. It had a beautiful history itself, involved a spy satellite being given over to NASA. It'll be a much bigger telescope, 2-meter telescope. So the first Euclid images are in. They're absolutely fantastic. They look great. And remember, what we're trying to do is just measure the distance between things and how lumpy the universe is. The way we do that is for every galaxy, we measure its shape and we measure how far away it is. Now you can see a nice galaxy here. That's a beautiful galaxy with high signal to noise. We need as many galaxies as we can get though. So we go all the way down to most of our galaxies look a bit like that. That one there, you know, these little blobs here. For those teeny tiny little blobs, the challenge is to measure their shapes to 1 part in 10,000 in a way that's statistically unbiased. So you can average them all out. I'll run through, I was going to talk about gravitational lensing. That's what the effect visually looks like. I don't have time for this, but this is the challenge really. The galaxies look beautiful, but by the time they get lensed, the effect we care about, and then they go through your telescope, and then they hit your detector and they get noise, they're really difficult to measure. You know, so the challenge now for the Euclid team is how do you take a fuzzy little blob like that, correct all of these effects, and measure that lensing signal. And so it's a big data challenge. We know what the end result will look like. So this is the current state of the art. This is an experiment called the Dark Energy Survey. We're a collaboration of about 500 people working on this for over 10 years, 15 years for some people. So this plot here may not look like much, but this is about 5,000 hours of person years has gone into this. And this is the state of art, and I'll just wrap up on this. So what this plot shows, on the x-axis, it's the amount of dark matter we have in the universe. So this affects the geometry of how things grow. In the top panel, this S8 quantifies how lumpy the universe is. The bigger S8 is, the more lumpy the universe. And this thing W is is a measure of what dark energy is and how its physics evolves. So let's start with this top panel. We see that there's a combination of the latest experiment from the early universe is Planck, an ESA mission. And at the time, it was combined with these constraints from dark energy survey to produce these purple plots. So in terms of how much dark matter we have and how lumpy the universe is, it's somewhere in that purple slot. Might not mean a lot to you, means a lot to me. Maybe the more interesting one is this one here. So the magic dotted line, -1, is dark energy as described by Einstein's cosmological constant, which is the most boring kind of dark energy model you could possibly imagine. There are hundreds of alternatives to this. And if W is anything but -1, it is an exotic piece of new physics that we've discovered, and there are Nobel Prizes going to be handed out for that sort of thing. Now, for dark energy survey, it's a little bit disappointing that we've landed on a circle right around -1. Now, when we designed Euclid, though, we were driven by W has to be measured to 2%. So our little circle is going to be much smaller, and it's up to nature, really, to put it where it does. If it puts it on -1, then, well, we're getting there. But if we find anything other than -1, it'll be huge. Thank you.
Thank you very much, Adam. I think we've got time for one question. You'd like to set up, Kevin? Yeah. Yes, got one here.
What does it mean if it's not -1?
Oh, wow, it could be.
It was a cliffhanger. Hang on.
It could be all sorts of things. Theoretical cosmologists are an incredibly creative set of people, and they have invented many, many models, quintessence models, all kinds, brain world models that will give you an answer that deviates from -1. The problem we really have is they all hit -1. So it's not only does -1 give us cosmological constant, it pretty much agrees with everything, right? Because all models allow that and then can take you away. But if you get anything other than -1, suddenly you've got a really exciting thing, and it depends on the exact value, which of these particular states of the universe do we exist in? Watch this space. Yeah, that's the way to do it. Yeah, as of next year.
Great. Thank you very much, Adam.